All right, so I'm making this for my friend Abitu, and we're going to go over this reversible processes and Carnot engine quiz. A Carnot cycle is shown in the diagram, during which process is heat removed from the system. So remember, Carnot cycles have kind of four parts to it. You have, well, two of the parts are your isothermic processes, and two of the parts are your what do you call it? I always forget how to, it's like adiabatic or something. During the adiabatic processes, no heat is entering or leaving the system. So keep that in mind. It's definitely not going to be one of those. How do we know if it's which of these are adiabatic? Well, adiabatic processes are not going to be isothermal. And so you can imagine like the shape for isothermal. Isothermal very rarely is as steep as like from 1 to 2 or from 3 to 4, but also to understand if it's to understand if it's adiabatic or not, it's gonna be it's very quick, right? So from something like from 1 to 2, from 3 to 4, you see a very sharp change because it happens very quickly, and as to not have any heat coming in or out. That's like a real world thing. They got to make adiabatic processes really fast. So I know it's from 2 to 3 to 1 or 1 to 4. How do I know which is which? Well, you got to think about for an isothermal process, there's no change in internal energy because temperature stays the same. So work is going to equal negative Q, or Q equals negative W. If you play around with the change in U equals Q plus W, we can find that W is equal to negative Q. Or I guess Q is equal to negative W. So if you have negative work, you have positive heat. If you have positive work, you get negative heat. So where is there positive work? It's when the volume is decreasing. So I would say from 1 to 4. Or from 4 to 1, whatever. Yeah, 4 to 1. That's a better answer. So Carnot cycle, same thing, same diagram, during which process does the average speed of the molecules decrease? When does the internal energy, that's what it's saying, or really technically the temperature. When does the temperature decrease? And it would be from either, so remember, it's not isothermal, it's one of the adiabatic ones. It's either 1 to 2 or 3 to 4. I would say this is kind of tricky. Actually, it's not too tricky. Your change in U is equal to W. There's no Q, so in an adiabatic process, so it's just W. So if you have negative work, you get negative change, you get negative internal energy. I don't know why I blank out sometimes. So I just need to see where do I have negative work, and that would be from 3 to 4, where the volume's getting bigger, so the work is done by the gas. Okay, engine has Carnot efficiency of 20%, 1,000 joules of energy is wasted. What are the two possible values for the work done by the engine? Carnot efficiency means kind of the maximum possible efficiency. So, why? I don't know why. Oh Lord, there are 6 options to choose from. So, 200 joules, that's 20% of it. Oh, that's a rookie mistake right there. You can't just say 20% of 1,000. That means 1,000 joules of energy is wasted. So, to kind of figure this out, what you could say is the work over your Qn is equal to your Carnot efficiency. So, work is the same thing. Well, Qn is equal to work plus Q out. So work is really Q in minus Q out. So Q in minus Q out is equal to work. Oh, wait. This is not how you want to do it. There's a better way to do it. I don't care about my Q in because I'm only going to be dealing with the energy wasted, which is 1,000, and the work, which is what we're solving for. So we can actually say work over work plus Q out equals Carnot efficiency. But Carnot efficiency is the max. So this is really, can be anything less than or equal to the Carnot efficiency. So it can't be more efficient than that, but it can be anything less than or equal to it. So in this case, you got to see, well, you could do some algebra, be like EC, oh god, plus wait, you could do some algebra, but honestly, I think I'm kind of overcomplicating this. You could just solve for what's the maximum amount of work that can be done. Maximum is when they're equal. So if you say, okay, you know what? Yeah, there's no need to derive an equation. I'm making this way more complicated. Also, Abitu said she hates deriving equations, so I can't. So work. If I know my Q out is 1,000. Actually, yeah, let's do it this way. Equal to EC. So work is equal to EC work plus Q out. And then work is equal to ECW plus ECQ out. And then we could solve for work. And then you get this is a pretty interesting equation. Work is so the max work that could be done is equal to E to the C minus 1 over E to the C times Q out. So in that case, it would be 0.2 minus 1 minus 0.2 times Q out. 0.2 over 0.8 is what, a fourth, I think? Is that a fourth? It is a fourth. So times that by 1,000. The max amount of work this thing can spit out is 250. 250 joules. So if it's 250 joules, it can be anything less than that. So you could have A to C, you could have B to C. Oh, you can only choose one. Let's go with, oh wow. You know what? I'm going to go with A to B because, it's hard to get perfectly 20%. But, yeah, there you go. I think A to C and A to B, or B to C I'd say A to B, though, just because 250, that's a perfect scenario. So it's probably going to be less than that. So in a given reversible process, the temperature of an ideal gas is kept constant as the gas is compressed to a smaller volume. So in that case, temperature stays constant. That means your internal energy stays constant. But the work is positive done on the gas because it's compressed to a smaller volume. You gotta have heat released to keep this thing isothermal, right? So just change in U equals Q plus W. Your change in U is 0. Your work is positive, so your Q must be negative. It must be heat being released. An ideal monatomic gas undergoes reversible compression to 1/3 its original volume. And which of these processes does the gas have the most work done on it? Ooh, that's interesting. At constant pressure, if the pressure increases in proportion to the volume, adiabatically, at constant temperature, if the pressure decreases in proportion to the volume. This is wow, okay. So it's a reversible compression. So constant pressure will not fly because, yeah, constant pressure won't work because isobaric is not irreversible, or is not reversible. Adiabatically seems tempting. Constant temperature is also interesting. I would have to throw away my thermodynamics for a second and say if the pressure increases in proportion to the volume, and the reason is because if you have more if your pressure increases, as you in proportion to the volume, then it might be decreases, because then if your volume gets smaller, your pressure increases, which means you need to apply overall a larger force over that distance when you integrate your FDX, your for work. This one's hard. Wow. Okay, I'm gonna think about this one some more later. Yikes. Okay. Welcome to AP Lang. Two identical samples or a monatomic gas are initially at a pressure P, of an occupied volume V. You perform two experiments which will both lead to the gas samples being compressed to the final volumes 1/3 as large as their initial. In one experiment, you make the gas undergo as isothermal compression. The other makes adiabatic compression. So oh, wait. I just figured out how you have to think about the graph. You have to think about the graph. This just like, as I was thinking about how to solve this one, I just realized, you got to think about the graph. So, let me, hopefully this recording isn't getting too long, but the main idea is that if you were to have your graph, it would be like, okay, this is your isothermal, this is your adiabatic. So we want, and it's really the arrows for these are going this way. So we want to see, well, what would be if work was, so we're looking at the curves as it's going this way, right? Like that way for the work done as the volume's getting smaller. So you can see like adiabatic would have a greater area. But then if you had a constant pressure, that would be smaller, I think. Yeah, that would be a smaller area. And then if you had something like this in proportion, so I'm thinking adiabatic actually. Let's try adiabatic. So for this one, which statement is correct? Adiabatic, we kind of showed, would lead to a higher final pressure. So I'm going to say the last one because it leads to a final higher pressure and the gas does not exchange heat. Let's see if that's true. I'm going to hope I get a 6 out of 6. Oh my gosh. All right. Hopefully this video helped make some things make sense there. And yeah, thanks for watching.